conceptual. Her current research focuses on conceptual abstraction, analogy making, and visual recognition in artificial intelligence systems. So Melanie is the author or editor of 6 books and numerous scholarly papers in the fields of AI, cognitive science, and complex systems. And in particular, her book, Complexity, A Guided Tour, published at Oxford University Press, won the 2010 Phi Beta Kappa Science Book Award and was named by Amazon as one of the 10 best science books in 2009. So her latest book is Artificial Intelligence, A Guide for Thinking Humans, published by Farrar, Straus, and Giroux. Some of our audience are big fans of your books, Melanie. So great pleasure to welcome you, and the floor is yours now. Yeah.
Thank you so much for inviting me. I will share my screen. And just to make sure, Alex, can you see that?
Yes, we can see
it.
It.
Yeah, I can. And I'm joining everybody downstairs.
Okay, thank you.
Yeah.
So I'm going to be talking about why AI is harder than we think. We've heard a lot about AI from the media in the last decade or so. We've gotten headlines such as computers are now better than humans at recognizing and sorting images. That, for instance, Google's AI can now caption images almost as well as humans. We've heard that we're going to have millions of self-driving cars taxiing us around by 2020. Well, that was 2 years ago, but we still haven't seen them. So why it's actually a lot of this media hype on AI has not really panned out as well as people might have thought. And here's a quote from one AI researcher: perhaps expectations are too high, and this will eventually result in disaster. Suppose that 5 years from now, funding collapses miserably as autonomous vehicles fail to roll. Every startup company fails, and there's a big backlash, so you can't get money for anything connected with AI. Everybody hurriedly changes the names of their research projects to something else. This condition is called the AI winter. This was actually a quote from Drew McDermott in 1984, when AI hype was again at its highest. Autonomous vehicles were being promised back then. As he pointed out, he's questioning whether they're going to roll, and indeed they did not. But this points out that this sort of recurring cycle in the field of AI of extreme optimism, followed by disappointment, followed by funding collapse or reduction, followed by a repeat of the cycle. So right now we seem to be in sort of the high point of AI optimism, but there are some cracks that are appearing in the facade of AI, imminent AI coming to infect every part of our lives. So some of these kinds of optimistic predictions are nothing new. Claude Shannon, the founder of information theory, said way back in 1961 that he expected that within 10 or 15 years, we'd see something coming from the laboratory that's not too far from the robots of science fiction fame. Herbert Simon, Nobel Prize winner in 1965, predicted that within 20 years, machines would be capable of doing any work that a man can do, man being the kind of sexist language of the 1960s. And Marvin Minsky, founder of the MIT AI Lab, said in 1967 that we thought within a generation, 20, 25 years, the problem of creating AI would be substantially solved. Well, none of those things actually happened in the time frame they predicted. And many years later, another pioneer of AI, John McCarthy, said, well, AI was harder than we thought. Indeed, it was. But it seems now that we're seeing a new sort of revolution in the field. and people are starting to make optimistic predictions. Even back in 2015, Mark Zuckerberg predicted that within the next 5 to 10 years, Facebook would see AI that was better than human level at everything. And Elon Musk, another tech billionaire, is predicting now that 2029, we're going to have AGI, or artificial general intelligence, and hopefully people on Mars too, as he said. So we're seeing these from sort of tech, tech billionaires, but we're also seeing from AI researchers, well-respected AI researchers, some similar sentiments. Rich Sutton, who's a well-known AI pioneer, predicted recently 50% probability of human level AI by 2040. And Stuart Russell, in his recent book, he's also another well-known AI researcher, asked, when would super intelligent AI arrive? That is more intelligent than humans. He thought it would probably happen in the lifetime of his children. And his timeline, he says, is more conservative than that of most AI researchers. Well, we all have seen, the great advances in AI and in vision and language, robotics, and other fields in AI. But these revolutionary technologies still have their limitations. They are susceptible to what I'll call shortcut learning, talk about that in a minute, adversarial vulnerability, and more generally, a lack of what we might call common sense. And so I'll be talking about some of these and why I think some of these issues are really going to temper the success of some of these optimistic predictions. So shortcut learning happens when a machine learning system, like a deep neural network, learns to do very well on a particular task, evidenced by its performance on a benchmark, but actually didn't learn the task the way the humans that are trained it thought it had. So here's an example from my own lab. A student in my lab trained a deep neural network to determine if a photo contained a picture of an animal or not. Okay, and so the deep neural network was trained on a large set of nature photos like these, with ones with animals, ones with no animals, and then was tested on a new test set of nature photos and did very well. But when my student looked into what exactly the machine had learned, which is actually not an easy task, this was his whole PhD dissertation, to figure out what it had learned, he found that it had, in many cases, been focusing on the background of the image rather than the foreground. And it was using the feature of a blurry background to predict whether there was an animal in the photo. Because it turned out, in this data set at least, the photographers, when there was an animal, had focused on the foreground, so the background was blurry. When there was no animal, these were all kind of landscape photos like this. The background is clear. And that seems to be a perfect way to predict whether the label is animal or no animal. So it hadn't learned to recognize animals. It had learned to recognize something easier to determine, blurriness. So this question of what did my machine learn can sometimes be answered with, well, it learned a shortcut. It didn't learn the actual task that it was being, the humans were trying to teach it. And this is seen in machine learning over and over again. This paper from 2018 did an experiment where a deep neural network that was very accurate on certain objects like school bus, was classifying that with 100% confidence. When these objects were photoshopped into unusual positions, the network was now certain it was a garbage truck, 99% confidence, or a punching bag, or a snowplow. Okay, so the title of the paper was, neural networks are easily fooled by strange poses of familiar objects. But what this is really showing is that the networks are using some features of the image other than the features that humans use to decide what the label is and with what confidence. So somehow it was seen this as a snowplow. Well, clearly there's snow there, but so maybe it was focusing on the snow. And, you know, they showed this with different kinds of objects like fire trucks being perceived as school buses now, and fire boats and bobsleds. So this shows an interesting vulnerability of neural networks, but this can of course have real world consequences if we're deploying these systems in the real world, such as, you know, when autonomous vehicles crash into fire trucks that they didn't recognize as such because they was stopped at a weird angle. Another limitation is adversarial vulnerability. This was first described in 2013 when in a paper called Intriguing Properties of Neural Networks. It turned out that you could take a neural network that confidently and correctly classified a particular photo, like school bus here, or temple here. So there's various labels that these were given. Engineers could then very carefully construct some perturbations to the pixels of the image. This is highly magnified perturbation. If you add this perturbation to the image on the left, it produces the image on the right, which to humans looks exactly the same. But this was engineered to cause the network to very confidently classify this as an ostrich. And the same with all of the images on the right. So this was called an intriguing property of neural networks, that you could adversarially attack them by adding very imperceptible perturbations to the image and make them classify the new image as any category you like. So it is an intriguing property, but it's also a very alarming property that these networks are susceptible to these attacks. So this sort of launched a new subfield of machine learning called adversarial machine learning. People showed in many different labs that you could manufacture patterns, like on these glasses frames that were manufactured by 3D printing a particular pattern, and using these glasses frames to fool facial recognition systems based on deep neural networks. So for example, one of the authors of the paper showed that, you know, the facial recognition system seeing him with these glasses were carefully engineered to make the facial recognition system classify him as the actress Milla Jovovich. So this just seems, you know, very strange, but it shows that the neural network is easily fooled by being perturbed by certain specially formulated patterns in the image. And it even goes so far as being a group that was able to show that by putting a particular pattern of stickers on a stop sign, they could fool a deep neural network vision system in a self-driving car to classify this as a speed limit 80 sign at many different distances and angles of the camera from the stop sign. And you can see where the top class that it was classified with very high confidence that this is a speed limit 80 sign. So these are called adversarial attacks on machine learning systems. And they really show that the systems are focusing on something that's not what we humans would think they should focus on. Finally, probably the most important limitation of a lot of these systems is their lack of understanding and what people call common sense. An example of this is that the most common accident involving self-driving cars is that humans rear-end them, because the cars will suddenly slam on the brakes for no apparent reason. The humans around them don't see any reason why they would slam on the brakes. And of course, humans tend to follow the next car too closely and slam into that next car. So, but it really reflects a problem with self-driving cars is that they don't have the common sense to figure out, say, what an obstacle is. They might consider a floating plastic bag to be an obstacle to slam on the brakes. Or here in New Mexico, we see this kind of scene, a tumbleweed, where a human would have the common sense to know that you don't need to stop for a tumbleweed in the road, but a self-driving car wouldn't. We know that if you drive up to a flock of birds, they're likely to fly away. You don't have to stop. And that this, say, snowman in the middle of the road is not going to run across in front of your car. These are all examples of sort of human common sense in somewhat unusual situations, especially this last one. These in the self-driving car literature are called edge cases. They're the kinds of situations that don't necessarily appear in the training data of the self-driving car because they're too rare. But there's so many possible edge cases in the world that if we have lots and lots of self-driving cars, some car is going to encounter some edge case somewhere very frequently. So we humans can deal with weird situations by using our common sense. We know how the world works. We know that snowmen won't run across the road. Here's an example of some problems with common sense from self-driving cars. Evidently a self-driving car, the camera looks at this car that has some pictures of bicyclists on the back. It's an ad for bicycles, e-bikes, but it classifies them as bicycles and people and would act accordingly. Or even more subtly, this person tweeted that his self-driving Tesla in its autopilot mode kept slamming on the brakes in this area for no reason. Why? Because it saw this billboard that had a sheriff with a stop sign on it, and it perceived this as a real stop sign. An interesting edge case, but one of the reasons why, one of the many infinite number of things that could happen that your self-driving car might not interpret correctly. So common sense has been called the dark matter of AI. That is, it's that thing that we ourselves in our humans, it's almost unconscious. You don't consciously sort of notice, oh, that's not a real stop sign. I don't need to stop for it. You just know that somehow because it's, about billboards and you can tell the difference almost unconsciously. But it's the dark matter because it's all around us, and yet we don't really understand how to give it to machines. There's a lot of work in AI on trying to teach computers common sense. Paul Allen, the co-founder of Microsoft, founded his own institute in Seattle precisely to teach computers common sense. And the United States Defense Department, which has long had an interest in AI, is putting a lot of funding into teaching machines common sense, but it's still very much an open problem. So recently I wrote a paper called Why AI is Harder Than We Think, which is about why people tend to make over-optimistic predictions about how close we are to human level AI or AGI or full AI or whatever you want to call it. And I talked about some fallacies that I think people, the public, the media, but also people in the field itself are susceptible to. The first fallacy is that narrow AI is on a continuum with general AI. So the idea is that these narrow AI systems like, say, AlphaGo, which was able to beat the best humans in playing Go, that's a narrow AI because it's only able to play Go. It's not able to do anything else. And we have lots and lots of narrow AIs around. We have facial recognition systems, which can recognize faces, but can't do anything else, and so on. And, this idea of general AI, which is something like a human that can do many, many tasks and can learn very quickly to do new tasks. This is really the it's the holy grail, if you will, of AI, that we're not there yet. But a lot of people think that if we have progress in narrow AI, that's going to mean near-term progress in general AI. So for instance, IBM talked about their Watson program, which you may remember playing the game Jeopardy, which was they called the first step into cognitive systems, which was their term for general AI. AlphaZero, which was a version of AlphaGo that could learn to play chess and Go, chess, and some other games. They called that the first step in creating real AI. GPT-2, the text generating program that was an ancestor of GPT-3, was called a step towards general intelligence. And these were called by the philosopher Hubert Dreyfus the first step fallacy. So that's where I got this fallacy. And he said that's the claim that if you make progress in AI on, say, a narrow task, any improvement counts as progress, that we're inching along a continuum towards general AI. But he says there's in fact a discontinuity in this assumed continuum. The unexpected obstacle is called the common sense knowledge problem. So here again, we have common sense. And his brother, Stuart Dreyfus, an engineer, made an analogy. He said, it's like claiming that the first monkey that climbed a tree was making progress toward landing on the moon. So the idea is that we have, with machine learning and deep learning and everything, we're at the top of a tree, but if we want to get to the moon, we have to climb down and build a rocket ship that can solve this common sense knowledge problem. The second fallacy I noted is that easy things are easy and hard things are hard. So sounds tautological, but what I mean is that we assume that things that are easy for us as humans will be easy for machines, and things that are hard will be hard for machines. So for example, we assumed that playing chess, because it's such a high pinnacle of human intelligence, playing chess at a grandmaster level, that if a machine accomplished that, it was clearly going to be able to accomplish all the so-called easy things, like, having a conversation or looking at a photograph and describing it. But that actually didn't happen. But many people in AI kind of are subject to this fallacy. Andrew Ng, another deep learning pioneer, said recently that he predicted if a typical person can do a mental task with less than 1 second of thought, we can probably automate it using AI either now or in the near future. So thinking that this whole, perception and all these things that we do very quickly and unconsciously, he thought would be easy for AI. And a little more subtly, Demis Hassabis, who's the co-founder of DeepMind, said Go is one of the most challenging of domains. So, but the question is, challenging for whom? It's certainly challenging for humans, but is it challenging it is one of the most challenging of domains for machines? Well, as the psychologist Gary Marcus pointed out, playing a game of charades, which any 6-year-old could do, is actually much more challenging for machines than the game of Go, because it involves things like language and theory of mind and common sense that machines don't yet have. This was summarized a long time ago by Hans Moravec, what's now called Hans Moravec's paradox, where he said it's always been comparatively easy to make computers exhibit adult level performance on intelligence tests or playing checkers. This was even pre-computer chess when he noted this, but difficult or impossible to give them the skills of a 1-year-old when it comes to perception and mobility. And I would add common sense. And in fact, giving machines the common sense of an 18-month-old baby is literally a grand challenge that the United States Defense Department has given for funding. My third fallacy was what I called the lure of wishful mnemonics. And I got that term from Drew McDermott, a Yale researcher, who wrote a paper in 1976 which he titled Artificial Intelligence and Natural Stupidity. And it's a great paper. I highly recommend it. He said, if a researcher calls the main loop of his program understand, he is until proven innocent, merely begging the question. He might mislead a lot of people, most prominently himself. What he should do instead is refer to this main loop as G0034 and see if he can convince himself or anyone else that that implements some part of understanding. And he says many instructive examples of wishful mnemonics by AI researchers come to mind once you see the point. And I think this idea that we're using human mental terms to describe what computers do, this kind of anthropomorphism turns into this kind of wishful mnemonics. So I've noted a lot of modern wishful mnemonics. You know, for instance, IBM, talking about its Watson program, said Watson can read all of the healthcare texts in the world in seconds. Using this term read, which in the human sense implies understanding what you read. But in Watson's case, really, it in truth was processing language in a very different way than humans process it. And actually, Watson wasn't able to understand healthcare texts or understand context and nuance in 7 languages, you know, using these terms, these human anthropomorphic terms. DeepMind said that AlphaGo's goal is to beat the best human players in the world, not just mimic them, saying the idea that a program actually has a goal, like a human goal. Or even in the benchmark data sets that we test our machine learning programs on, we call them by names like reading comprehension or common sense understanding or general language understanding evaluation. These are names of actual data sets that machine learning programs have in all cases surpassed humans on. So we get reports in the media like Google's machine learning has now exceeded humans in reading comprehension or language understanding. And really what's happening is that these benchmarks don't actually test the general task that they're named after. And so the machines that can do well on these benchmarks have not actually accomplished these tasks, but we end up fooling ourselves and thinking that they have. Or even more profoundly, you know, we call our methods deep learning, even though these systems do something very different from human learning or neural networks, you know, implying that the systems have something to do with the brain, which in fact, they're actually very far from the way the brain works. And my last example, when we're describing what machines have learned, we often use human level terms, which is, you know, what psychologists in animal cognition call over attributions. So here's an example of that. DeepMind, one of the first things they worked on was getting machine learning systems to play Atari video games. So they had a reinforcement learning system they called DQN, Deep Q Network, that learned just from observing the pixels of the video and taking actions. So in this game, Breakout, you move a paddle, it hits a little ball that then if it collides with one of these bricks, the brick will explode, and you get more points for exploding the higher bricks. And so here's what their system learned to do just by observing the pixels, taking actions, and observing the rewards that it got via points in the game. It says after 600 episodes of learning, DQN finds and exploits the optimal strategy in this game, which is to make a tunnel, that is, you know, knock out all the bricks here around the side and then allow the ball to hit blocks by bouncing behind the wall. So that the ball just bounces off. You don't even have to move the paddle. It just bounces off the wall and hits bricks. Okay, but notice in red, these human concepts, tunnel, ball, blocks, wall. DQN has only seen the pixels. It hasn't been given these concepts, but DeepMind, in using this description, is giving us the feeling that the system has learned such concepts. Well, if it has learned such concepts, it should be able to transfer them to very similar kinds of games. So here's a paper. Here's a paper that came out in 2017, which showed that if you take a deep reinforcement learning system that's—
Melanie, our screen has gone to a sleep mode. We're just waiting.
Oh, okay. I can wait for a second if you want.
Just a few seconds.
Sure. Is it working now?
Yes, it is working now. Yeah.
Okay. So here on the left, you see a depiction of a standard version of Breakout, just what I showed you before with the colored blocks. But then they tested the same network that had been trained on this system and could do that tunneling strategy on a version in which the paddle was moved up by a few pixels. That's the only difference. But it turned out that the version that had been trained on the standard Breakout could not accomplish that same strategy with this new version, because somehow it was using configurations of pixels to that allowed it to accomplish that strategy on the left. Those same configurations were not present on the right, even though conceptually, if you knew concepts like tunnel and wall and ball and paddle and so on, you would certainly be able to do that the same thing here. So it really hadn't learned those concepts. The final fallacy is that intelligence is all in the brain. Okay, this is something that has been assumed in AI for its entire history, that we can get general intelligence basically using the computers on our desktops, perhaps connected to the cloud, but no body needed. This idea of a brain in a vat that's attached to sensors that are then being output or input through a computer interface. This is sort of what the metaphor for what current AI is. And many people have said that really all we have to do now is capture the computational power of the human brain, comparing AI with human brain, and ignore anything about the body in order to accomplish AI. But this goes against a lot of work in cognitive science, which shows how our bodies are intimately connected to our brains and are a source of cognition, as is our social interactions and our cultural embeddedness. And so it's not clear that this brain in a vat metaphor will ever get us to general AI. So let me just summarize some of the open questions that I think are spurred by these fallacies. If narrow AI is not on a continuum with general AI, how can we actually assess progress towards general or human level AI? How do we know how close we are? If easy things for humans are not easy for machines and vice versa, how do we assess the difficulty of a domain for AI? How do we talk to ourselves about what machines can and cannot do without fooling ourselves with wishful mnemonics? And finally, how embodied and socially, culturally embedded does intelligence need to be? I don't have answers to these questions. I think that we really need a better kind of theoretical science of intelligence, not just human intelligence, but intelligence in general, to start answering these. But I don't think we'll have a realistic view of how close we are to human level AI without being able to answer these questions. So I talk a lot about this kind of thing in my book, AI, A Guide for Thinking Humans. And thank you very much for listening. Happy to answer any questions.
Yeah, camera is on.
Oh, camera is already there, yeah.
Thank you.
Melanie, can you see the audience from your
Kind
end?
of. I can see they're very
Right.
distant.
Because we can't see it on this screen. So,
Jesse, I can show the background.
anyway, so it was great talk, absolutely. Fantastic. So, and I'm sure that there will be some questions here from this audience. And guys, we've got time, so please, yeah.
Alexander.
So, I'm sorry, there's also some questions on Zoom. Should I call on those people?
Yes, please.
Yes, please, yes.
Okay, so Alexander has his hand up.
Hello, this is Alexander, University of Edinburgh. I remember reading, I think Douglas Hofstadter was your PhD supervisor, wasn't he?
Yeah.
He wrote quite an interesting book. What was it? Creative Concepts and Fluid Analogies, something like that. So is that sort of the solution? Because reading through that book, I was scared at how right on the money he was, at least according to my understanding of the field.
Yeah, I think that getting machines to make analogies, to make abstractions, to have kind of more rich concepts is part of the solution. It's something that is still, I think, understudied in AI, but it's something that I'm personally really interested in working on. So yeah, absolutely.
Thanks.
Cliff now, yeah, Cliff Jones. Cliff.
So super talk, thank you very much. I don't work in AI, but I found it very enlightening. In response to your first challenge on that final slide, to what extent do you think we should make the requirement that an AI system can explain its behavior, a criteria for movement forward?
Yeah, that's a difficult question because, you know, who is it explaining it to? Is it explaining it to its programmer, or is it explaining it to sort of the average person? And this is something that's come up over and over again. You know, there is a whole subfield called explainable AI, which is trying to get machines to either be more transparent about how they make decisions, or, as you say, explain themselves. And it's very difficult. And it's difficult to say like what counts as a good explanation. But you know, I do think that we have to have more transparency if we're going to be using these systems in ways that affect human lives. You know, I was recently at the airport, and they were using facial recognition for, you know, instead of your boarding pass. And say we know that facial recognition systems can be biased by skin color, by gender, other factors. So how do they, you know, if you're being denied boarding on a flight, you need an explanation for why, and, you know, just to understand that and to fix errors. So, but it's still a big question of how we get these incredibly big, complicated deep neural networks, which kind of power these applications. How do we explain what they do when even the people who created them don't understand how they work?
Questions from our audience? Steve, please.
So I was going to ask, you obviously say that, you know, there's a lot of hype from, you know, different people, you know, sort of either, you know, the tech entrepreneurs or, you know, the newspapers. As AI researchers, should we be effectively trying to downplay this overhyping of the area? And do you think that would actually work?
You know, it's yes, we should be downplaying it. And I actually, you know, I don't know if you all followed this story about the sentient chatbot at Google that happened over the last few days. But, you know, I and other AI researchers have been on all kinds of media trying to downplay that. But it's often a losing battle because AI, so much of AI now is controlled by big companies that want to use it commercially. And so they obviously want to promote their systems and hype them, as we saw like for IBM doing it's hyping its Watson system. So it's hard to fight back, but I do think that's an important part of science communication, that we have to talk about what are the real limitations of these systems.
Matthew, please come up here.
So I had a question. It was almost on that topic. But when you talk about, like, say, hyping systems, so if you have a narrow AI system that's, I would say, it's relatively easy to, if you're pitching that to investors, you can say how that can be exploited, relatively speaking, in the short term. But for generalized artificial intelligence, you're talking about a real long-term problem, which essentially should solve everything. But if you're pitching that to somebody for money, you're essentially saying, I need funding for the next 50 years. I was wondering whether or not we could talk about whether or not that's actually part of the problem, that people don't make this distinction. 20 years ago, it was really, really clear. Everybody made a distinction between generalized artificial intelligence and what is effectively pattern, like machine learning or different terms. But now everybody just uses blanket terms, and especially in industry, you see this massive amount of hype. Which, I mean, we're on the third cycle of this neural network hype now. I was wondering if you could explain basically the difference between the time delays. Like how do you get people to realize that generalized stuff, if it was to happen, would change everything? Therefore, it's very unlikely to happen.
Well, even within the AI community, as I showed there's disagreement about sort of the timescales. A lot of very, very good AI researchers believe that just scaling up the kinds of systems we have now, going from 1 trillion parameters to, 100 trillion parameters, which maybe could happen, is going to get us there to general AI, and that we can just happen over the next decade or something. So I don't know. People disagree so much. It's hard to say that this is really going to take a very long time, and we're not that close to it. But it's something that's plagued the field forever. So it's nothing new. This kind of hype and this kind of assumption that intelligence is something to be solved, and it will be solved in the next 10 to 25 years. So I don't really know exactly what to say there, but it's something that we all grapple with.
I have a question. Do you think general AI is a superset of narrow AIs, or is there a different approach to this?
Yeah, I think it's quite different. General AI implies not just kind of having a big library of narrow AIs that you can call on, but also kind of knowing, just essentially even knowing what is the problem that you're trying to solve. A narrow AI knows it's trying to play Go, or it's trying to do speech recognition, or it's trying to do, some other thing. But faced in a situation, what is the thing you're supposed to do? What is the task? That part of it, intelligence, is knowing that. And also being able to take something you learned in one task and apply it to another task that might be, analogous or something. All of those things go beyond just having this idea of having like a big library of tasks and picking from them and picking from narrow AI. So I do think general AI is something qualitatively different.
Hello, can you hear me?
Yes. No. Would you like to?
So,
wake up a bit.
That AI expert that we ever achieve full autonomy in next 5 years or in our next decade.
I'm sorry, could you just repeat that? I couldn't hear the first part.
Sorry?
I think I better put my jumper on, don't
Yeah.
Someone in the virtual
I don't
meeting,
think so. It's warm.
mute your microphone, please.
No.
Could you all mute your microphones, please? Thank you.
Yeah, okay. As an AI expert, do you think that we will ever achieve full autonomy, or in maybe, by 2025, or less than in next 1 decade, or will we ever achieve this? Because I have been following some AI researchers who are, closely working on this, and like AI experts are on both sides of this, something that, is possible, something that, it's not. So what are your thoughts about this? And yeah.
By full autonomy, do you mean like in driving?
Yeah, sorry, autonomous vehicle. Yeah.
No, I don't think we'll have full autonomy in 5 years or even 20 years. I think what will happen is that we humans will adapt our infrastructure, our roads, our mapping of roads and cities and so on to what self-driving cars can do, as opposed to self-driving cars being able to get much, much better. You know, we see that in all technologies. We adapt our infrastructure as much as to the technology, as much as it adapts itself to us. So, you know, I think we'll have self-driving cars that can operate in certain kinds of situations in certain parts of cities, with some backup from humans if needed. Like people have talked about, you know, having like humans remotely teleoperating cars if they need to get out of trouble. It's kind of like a drone. So I think all of that will enable self-driving cars to be autonomous in some situations, but I don't think we'll have full autonomy, meaning that a car can do anything that a human, you know, driver can do.
Okay. Yeah, right.
Great. It's a great topic, actually. Yeah, we should be more AI friendly in a way, yeah, isn't it? So in the future. Well, Nick, please. Yeah. So could you please disable your mics who are online, please? Yeah.
Thank you firstly for a lovely talk. My question is about common sense. So my mother tells me that I don't have it. She says that she dropped me on my head when I was a baby and I destroyed that part of my brain. And I've always, but my question really relates to, I've seen some fascinating functional MRI scanning where certain mental tasks show up as activities in MRI scans, and you can see a certain specific area of the brain associated with that task. Do you know if common sense has similar common physical signals in the brain, or has that never been investigated?
You know, I don't think common sense is a well-defined enough thing to look for it in the brain. It has so many facets. You know, people have looked at aspects of it. So one aspect of it is what people call intuitive physics, meaning you know what objects are and you know how objects interact. And so, like, you know, babies have to go through this developmental stage where they know that they learn that if an object is hidden behind like some kind of other object, it still exists. Call that object persistence. So people have looked in the brain for things like how that works. But I think common sense is just such a broad area itself that we can't really, it's kind of a placeholder term for more precise mental ideas. But the idea of trying to get inspiration from how babies acquire common sense is exactly what a lot of people are trying to do right now, to give machines the same kind of learning environments and kind of innate concepts that babies have.
Maybe there's still some hope for me. My common sense may still be in the brain somewhere.
It may still be there, yes.
Yeah, a couple of questions from our PhD students. Jesse.
Surely part of the problem as well when it comes to general AI is a lack of what the problem actually is. Because when you think about normal machine learning, normal AI, we always have this idea, this is the problem, this is how we fix it, and a metric of measuring how you fix it. Surely with general AI, there's no real metric, there's no real problem in the first place, because how do we judge what we are doing in the beginning? Because we don't know what common sense really is to define how we do common sense. So where's the starting point for anybody to shift towards what we're going to do for general AI? Because if we can't assimilate the problem itself, how do we measure how far we can get or what we can do?
That's a great comment. I totally agree. I think we don't know exactly what the problem is, what sort of the target is, if you will, of the research on general AI. We know that we know some aspects of it, and but we don't, people define it differently, and it's not a sort of a thing you can write down formally as an objective function like people do in machine learning for specific tasks. So I think you're right. I think we need a better kind of interaction between people thinking about intelligence more generally in all kinds of systems and trying to understand like what general intelligence might mean, or even how general we humans are. We're not totally general ourselves, either. So I think you're completely right.
Right. Shang-Chi, please.
Well, as a hardware architecture designer, I'd like to know that, do you agree there exists a best architecture for the AI generation? Because I read lots of papers about the accelerator design for different kinds of machine learning cases. And I think on the Earth, like the human brains, lots of animals have brains, but only the human brains win out in the intelligence development. So I'd like to know your opinion about whether there exists a best architecture of the hardware for the AI.
That's a hard question. I don't think we know at all. So, we have these neural networks, these deep neural networks, which have many layers of simulated neurons. But one thing about them is that's very different from the brain is that they lack a lot of feedback. It's really a feed-forward architecture, and the feedback connections are just very minimal or missing entirely. Whereas we know in the brain, there's as many or more feedback connections than there are feed-forward connections. So that's one kind of architecture question. How could we make a system that could effectively use that kind of feedback? The whole hardware thing there's all this sort of neuromorphic computing hardware that people are building now that use things like spiking simulated neurons as opposed to non-spiking, which is what we have in most neural networks. And there's a lot of debate about how important that is. But I think we just don't know, because we don't know what the right architecture is for these AI systems.
Final question from Faye.
Faye, final question.
Sarah, do you want to?
No,
Thank you for your talk. A few years ago, I think almost 10 years ago, I attended a conference where leader of a company stood up and said that was about self-driving cars. He said that his ambition was to take out the driver because driver error in that year caused over 1 million deaths worldwide. And that if we took out the driver, we put a machine in, we had 1 million fewer deaths. So that was his ambition. But obviously there were errors where the machine where the human wouldn't have made. But my question is, do you know if machines would not make those 1 million errors that humans typically make? And if we replace humans with machines, in the near future, would we have a net reduction of deaths? Okay, there will be some atrocities where the human wouldn't have done that. But worldwide, we have a reduction of deaths. Wouldn't that be worth it? Or wouldn't happen? Or what's your estimate?
Yeah, no, I'm not really an expert on that. But I do think, if we somehow magically replaced every human driver with an autonomous car, clearly we'd have many fewer accidents. One of the problems is the autonomous cars having to deal with a world in which humans are also driving and humans are walking across the street and there's pedestrians and all of that stuff. So how many, it's not clear sort of how these two kinds of drivers can successfully interact on the roads. That there's a lot of debate, but I think you're right. I think eventually we will hopefully reduce huge amounts of accidents via autonomous cars, but there's a lot of hurdles to get through before that's going to happen. The hurdles are not all technological, they're also social. They're things like figuring out who's responsible for an accident with a self-driving car, and how do you insure these things, and all those kinds of sort of socioeconomic questions. So those are as hard to solve as the technological issues, I think.
Right. Yeah. Thank you. What my hypothesis is that I don't have any evidence. Is that the self-driving cars are already saving more lives than they're killing.
But yeah, that's hard. I don't think that it's. I don't think that data is easy to get.
Drive in India. We will
Yeah. Yeah, I don't know. There's probably not enough data to really test that hypothesis, but it's possible. I don't know.
Thank you.
Thank you very much. Well, I should thank everybody at this point. And before we close down, I would like to thank Sarah Olson, who helped us to connect with you, Melanie, because Sarah is your relative and she happens to also be interested in AI. And thanks to you, being relative of Sarah, that you taught Sarah some of the AI issues.
Thanks, Melanie. I really did want to say thanks so much for coming. It's brilliant to hear about your work finally. And also thank you for sharing it with my colleagues and staff here. It's really appreciated. It was great.
Well, thanks. Thanks, Sarah. Thanks for arranging all this. I really enjoyed it.
I definitely hope to speak to you again.
Well, fantastic. Yeah, so, well, let's thank Sarah. Great pleasure and success. Well, I'm sure we will start reading your books even more in terms of the audience. Yeah.
Thank you so much. Bye-bye.
Thank you. Bye-bye.
Thank you.
They will be recorded. Yeah, I'm thinking that. Let's be careful. The thing is, to get through these reviews,